building envelope design, which aims to achieve the maximum comfort with the minimum primary energy consumption and thus to minimize greenhouse gas emissions, requires that the parameters of comfort and energy are integrated into each of the critical steps of the design process. Factors such as climate, master plan, building shape, facade design, the thermophysical characteristics of the materials, and finally the building plan must play a role in decisions. In this lesson, we will discuss the most important issues related to the energy efficiency of the building envelope and design strategies. Marcus Vitruvius Polio, a philosopher and architect, has stated long time back about building design. If our designs for private houses are to be correct, we must at the outset take note of the countries and climates in which they are built. One style of house seems appropriate to build in Egypt, another one in Spain, a different kind in Pontus, one still different in Rome, and so one with lands and countries of other characteristics. This is because one part of the earth is directly under the sun's course, another is far away from it, while another lies midway between these two. The building envelope is the physical barrier between the exterior and the interior environments, enclosing a structure. The building envelope comprises opaque elements, walls, roof, foundation, and doors, and transparent elements, glazings, and any other penetrations. To design a low energy, comfortable building, it is necessary to define a planning strategy depicted in this figure, which shows that maximum effort must go into minimizing the amount of energy needed by means of appropriate architectural design, therefore, must be focused on the energy efficiency of the building envelope. Sustainable site planning begins with an assessment of the building site in terms of its capability to provide natural resources such as light, air, and water, and the extent to which the existing natural systems will be required to support the new development. Solar analysis is pivotal to exploit winter solar gains, to design solar shading systems, and to convert solar energy into useful electricity, thermal energy. Wind analysis is pivotal to assess natural ventilation potential, outdoor comfort, and the possibility to produce renewable electricity. As regard to building envelope design, building shape and orientation must be the first choices in the design process because they have the most impact on thermal and visual comfort and energy consumption. Another important decision is related to the thermal insulation and the thermal mass of the envelope, together with the sizing of glazed elements. Moreover, the building design should also take particular account of solar control and the natural ventilation to contrast the high cooling demand and overheating risk during the hot seasons. The shape factor is quite critical since the capability of a building to store or release heat is related to its volume and to its mass and shape. Losses and gains take place through envelope surfaces. Thus, the ratio of surface to volume S divided by V determines the heating rate during the day and the cooling rate during the night. At a constant volume, heat losses and gains increase, moving away from the more compact form, the coupe. The general rule is minimize SV ratio and avoid complex shapes, as evident from this example. The heat transfer, thermal flux, across the opaque envelope directly depend on the level of insulation, which is characterized by its thermal transmittance, U value. Current projections on the increase in the cost of energy indicates a very close dependence between the level of insulation of the building and the cost of heating. The design choices at an early design stage have consequences for many years. To decrease the heat loss it is essential to increase the thermal resistance of the envelope, improving the level of insulation. The effectiveness of this strategy, however, decreases with increasing thickness while increasing cost. This figure shows the limit values of thermal transmittance of envelope components for different climatic zones under the implementation of EPBD in Italy. This figure shows the profile of indoor and outdoor temperature. The heat flow across a wall is not constant because the outside air temperature changes in a cyclic pattern throughout the course of the day. So the heat capacity also comes into play, and the heat flow through a wall varies over time in different ways depending on the resistance and the specific heat capacity of the material. It can be noted that the actual heat flow curve is delayed behind the zero mass curve by some time. This delay of the peak is defined time lag and is measured in hours. The actual peak heat flow, when mass is taken into account, is also reduced by the effect of the mass, and this effect is added to that due to thermal resistance. The ratio of the real wall peak heat flow to that of ideal wall with zero mass is defined decrement factor. This figure shows the positioning of insulation and related thermal performance features. In air-conditioned buildings, a certain amount of insulation and thermal mass is always recommended in order to reduce heat flow and to even out the effect of the changes in external energy inputs like solar radiation, temperature, and wind. In the absence of an air conditioning system or in the periods in which it is not used, the optimum amount of insulation and mass of walls and roofs depends on the type of climate. Solar gains through the glazings are controlled most effectively with sunsets outside the windows as shown in this figure. Horizontal shading devices are the optimal choice for north and south facing facades. Horizontal overhangs located above the windows on the north and south facing facades are very effective and should extend beyond the width of the window to shade it properly. Horizontal overhangs on the east and west facing windows need to be very deep for protection in the early morning and in the late afternoon and are not recommended. East and west facing facades are harder to protect than those facing north and south because of the low position of sun in the morning and in afternoon. Vertical fins are usually recommended for east and west orientation at latitudes above 40 degrees. An appropriate shading device for east and west orientation in the tropics is the egg crate type. General rules about the glazing envelope design can be summarized as: minimize the amount of glass. So window to wall ratio WWR should be less than 20%. More glass means more energy consumption and cost. Always use shadings. Horizontal overhangs are perfect on south facades. Movable shadings have high performance but could be expensive. Use solar control glazing when shadings are not applicable. As we have seen, building envelope has an important role in minimizing the energy demand for heating and cooling. Therefore, it is of utmost importance for building energy efficiency.